Good afternoon, students. This is Aravind, Assistant Professor, Department of Triple DBSIT KAVALI. So, in the previous class, I discussed about some comparisons between Statcom and SVC. So, in actually, I am listed so many comparisons between those SVC and Statcom. So, in that one, I explained about VA and VQ characteristics of Statcom and SVC. And now, in this class, I'm going to discuss remaining comparisons between SVC and Statcom. So, in this class, I'm going to discuss the first comparison is transient stability. So by using this transient stability comparison, I will explain how it differs STATCOM with SVC. So actually in the STATCOM, the ability of the STATCOM to maintain full capacitor output current at low system voltage, so also makes it more effective than the SVC. Okay, so the ability of the STATCOM to maintain full capacitor output current at low system voltage also makes it more effective than the SVC in improving the transient stability. That is the first swing. Okay, you know already the transient, what is meant by transient stability. So the transient stability is the ability of the system to bring it to a normal or stable condition when a large disturbance occurs. That is known as transient stability. So the effectiveness of the STATCOM in increasing the transmittable power is illustrated in this figure. So I will show the diagram. So these two gives the characteristic diagram between transmitted power P versus transmission angle phi of a two machine system with a midpoint STATCOM. Okay, STATCOM, and at the same time for the SVC also. So in the left side we have STATCOM diagram, and on the right side we have SVC diagram. Both are at the midpoint. So here we have the circuit diagram also. Here we have the circuit diagram also. Okay, by using this, I am drawing this diagram. Okay, so by using this diagram, we will explain the comparison between these two. So here, the effectiveness of the STATCOM in increasing the transmittable power. So where the transmitted power P is shown against the transmission angle delta. So for the usual two machine model. So actually in this case, I am taking two machine system. Okay, so that's why here we are using two machine model at various capacitor ratings. So defined by the maximum capacitor output current, that is IC maximum. That is the maximum capacitor output current, IC maximum. So for comparison, an equivalent P versus delta relationship is shown on SVC, that is in the figure B. So this one. Okay. So here, if you observe this one, I am taking the angle delta between 0 to pi and the power between 0 to 2.5. Actually, I am taking the power values in per units. Okay. So that's why I am taking 0 to 2.5. So here these are the different curves we have at different levels. Okay. So if you observe this one, we have P is equal to V square by X into sin delta plus V into I naught maximum by 2 plus sin delta by 2. So this is for all the three curves, and we have P is equal to V square by X sin delta. That is for the dotted line curve. We have half sine wave. So this is for that one. Okay. So here we have P is equal to V square by X and P is equal to 2V square by X into sin delta by 2. So these are at I naught maximum 1 and I naught maximum 2 and at I naught maximum 3. And coming to the SVC, so in this one also I am taking the different curves, but here I am taking the BC maximum 1, BC maximum 2 and BC maximum 3. That is the flux density, maximum flux density. Okay, so here P is equal to V square by X by 1 minus X by 4 sin delta. So that is P naught is equal to V square by X and P naught is equal to 2 into V square by X into sin delta by 2. Okay, like this we are drawing the curves. Here I am taking totally 4 curves. In those 4 curves, one is in the dotted line representation. So that is normal power, that is P is equal to V square by X into sin delta. Okay, like that we are drawing the characteristic diagram. And after that, so from the observation of the diagrams, the STATCOM just like the SVC, but behaves like an ideal midpoint shunt compensator with P versus delta relationship. That is in the previous diagram. So from the diagram, we can observe that STATCOM is just like SVC. That means it behaves like an ideal midpoint shunt compensator with P versus delta relationship. So actually, this concept I already explained in the objectives of shunt compensation. Okay, In that one I also discussed. So from that section I am taking the equation that is P is equal to 2 into V square by X into sin delta by 2. This is for until the maximum capacitor output current is reached. Maximum capacitor output current IC maximum is reached. So from this point the STATCOM keeps providing this maximum capacitor output current that is independent of further increasing the angle delta and the consequent variation of midpoint voltage. So why we are using this midpoint voltage means, so in this configuration I am using the midpoint connection only, that's why I am taking the midpoint voltage. So as a result, the sharp decrease of transmitted power P in the pi by 2 less than delta is less than pi region, that is pi by 2 pi region. So characterizing the power transmission of an SVC supported system, so is avoided and obtainable with the integration of P with d delta area representing the improvement in stability margin is significantly increased. So like this manner we have to take these transition stability conditions. Next, if we increase in the transition stability margin obtainable with the STATCOM over a conventional thermistor controlled SVC of identical rating is clearly illustrated with the use of previously explained. Actually, previously we seen two diagrams. Those two based on the equilibrium criterion concept. So here also I will take the two diagrams. So these two. So these two are the improvement of transition stability obtained with a midpoint STATCOM. That is for STATCOM is for the diagram A and SVC for the second diagram. Okay. So by using these equilibrium criterion concept, so here I am taking the two simple two machine system. So it will give the basic shunt compensation principles is compensated at the midpoint by a STATCOM and an SVC of the same VAR rating. So that means for the sake of clarity, it is assumed that the system transmitting steady state electrical power, that is P1 at angle delta 1 is subjected to a fault for a period of time during which P1 becomes 0. So at that time I am taking these conditions, that is steady state electrical power P1 and angle delta 1 is subjected to a fault. So the diagram is like this. Okay, so similar to the previous diagram. So actually I shown two diagrams for the improvement of transition stability for the same case, but here also I am taking the conditions, but here I am considering the equilibrium criterion concept. So in this one, for the same curves, what we seen in the previous diagrams, same curves we will take, but one difference is there, that is here I am taking the equilibrium criterion concept. That's why here I am taking margins and areas. So here I am taking the shaded areas. Okay, shaded areas I am taking. One is A1 and another one is A2. In this one, A1 is the accelerating area and A2 is the decelerating area. So in the both diagrams, same procedure is follows. Okay, in the two diagrams, I am taking the equilibrium criterion concept. That's why I am taking the areas. Okay, here the angle is changes from delta 1 to delta C in both SVC and STATCOM. We have the curves like this. Here we have IC maximum 1 and IC maximum 2 and IC maximum 3. And coming to the SVC, in that one we have BC maximum 1 and BC maximum 2 and BC maximum 3. Like that we have the curves. Okay. It is for the given VAR rating. And during the fault, so during the fault, the sending end machine accelerates. Okay. During the fault, actually we have three conditions. One is for pre-fault condition, and another one is for during the fault condition, and another one is for post-fault condition. So here I am taking during the fault, the sending end machine accelerates. That means it is observing the kinetic energy. It is observing the kinetic energy represented by the shaded area below the constant P1 line. That is this one. So this one, P1 area. So this one. Okay. So P1 line and increasing this angle from delta 1 to delta C. That means delta C is greater than delta 1. So if you observe this diagram, you will understand. So here I am taking two shaded areas. So the below to the one value we have one area, and above one point we have another area. Okay. So here the angle changes from delta 1 to delta C. Okay. Next, thus when the original system is restored. So when the original system is restored means after fault clearing. So original system is after fault clearing, there is nothing change in the curve. So that means when the original system is restored after fault clearing, the transmitted power becomes much higher than P1. Okay, the transmitted power becomes much higher than P1 at which condition? So after fault clearing condition. Okay, due to larger transmission angle, that is delta C. Okay, due to larger transmission angle delta C. So as a result, sending end machine starts to decelerate. So actually, during the fault condition, the sending end machine accelerates. But after fault clearing, the sending end machine starts to decelerate. But delta is increases. So in the previous case also, the delta is increasing. In this case also, the angle delta increases further until the machine loses all the kinetic energy. Okay, further until the machine loses all the kinetic energy. That means it gained during the fault. So whatever the energy it is absorbing in the during the fault, so after the loss of this kinetic energy, we have the sending end machine starts decelerating. Okay, like this I am taking. And next, the recovered kinetic energy. That means after the during the fault, we have some energy. Okay, so it is cleared after the clearing the fault. So that's why the recovered kinetic energy is represented by the shaded area between the P versus delta, that is power versus angle curve, and the constant power line P1. Okay, this one, this area, this is the accelerating area that is above 1 point. Okay, so the remaining unshaded area below the P versus delta curve. So actually we shaded two areas only, but the remaining one is unslotted. That means the unshaded area that is below the P versus delta curve and above the constant power line, that is P, provides the transient stability margin. So the unshaded area all gives the transient stability margin. So as can be observed that from the diagram, the transient stability margin obtained with the STATCOM due to better support of the midpoint voltage is significantly greater than that attainable with the SVC. That is, in this one, the transient stability margin is obtained is higher than compared to the SVC of identical wear rating. So this is of course means that the transmittable power can be increased. That means if the shunt compensation is provided by STATCOM rather than by an SVC. So at that time the transmittable power can be increased compared to SVC. So for the same stability margin, the rating of the STATCOM can be decreased below that of the SVC. Okay, like that we are taking. So up to now we discussed about the comparison between static version composite, that is SVC and STATCOM, that too in the transient stability condition. And next I am moving to the second one, that is response time. Okay, so before going to this response time concept, so as demonstrated in previous sections, so in the previous section, that means characteristics of static compensators. So in that one, the attainable response time and the bandwidth of the closed voltage regulation loop of the STATCOM are also significantly better than that of the SVC. So the attainable response time and the bandwidth of the closed voltage regulation loop of the STATCOM is significantly better than SVC. So although the closed loop voltage regulation of both compensators can be expressed by the formula, that is delta Vt by delta V, that is equal to 1 by 1 plus G1 G2 Hx. So actually this equation I derived in the previous class, that is the characteristics of SVC and STATCOM. So same thing I am taking here. So that is delta Vt by delta V, that is equal to 1 by 1 plus G1 G2 Hx by using the transfer function and dynamic performance concept in the characteristics of STATCOM and SVC. So here the time constant T in the transfer function G2 is about an order of magnitude similar for the STATCOM than it is for the SVC. So that is, it is typically from less than 200 microseconds to 350 microseconds for the STATCOM and 2.5 to 5 milliseconds for SVC. Like that, the magnitude is smaller compared to the SVC. Okay, next. So considering the rapidly changing angle versus frequency characteristic of the e power minus TDS term. So here I am considering rapidly changing angle versus frequency characteristic of the e power minus TDS term. So this improvement is important from the standpoint of attainable frequency bandwidth. So that means the practical importance of wide frequency bandwidth cannot be overstated for applications requiring faster responses. But even in typical transmission applications, the STATCOM can provide stable operation with respectable response over a much wider variation of the transmission network impedance than is possible with the SVC. That means overall we will say that the STATCOM is better than SVC. Okay. So next I am going to next comparison, that is capability to exchange real power. So this is the fourth comparison between SVC and STATCOM, that is capability to exchange real power. So for applications requiring active, that is real power compensation, it is clear that the STATCOM in contrast to SVC can interface a suitable energy storage with the AC system for real power exchange. Okay, so here I am taking the real power compensation. It is clear that the STATCOM in contrast to the SVC can interface a suitable energy storage. So by using the STATCOM, we are using a suitable energy storage with the AC system for real power exchange or active power exchange. So that is, the STATCOM is capable of drawing controlled real power from an energy source. So energy source is nothing but the large capacitor, battery, fuel cell or superconducting magnetic storage, etc. Like this we are using energy source for the controlling the real power, and it's a terminal and deliver it has AC power to the system. So it's a DC terminal and deliver it has AC power to the system. Next, it can also control energy absorption from the AC system to keep the storage device charged. Okay, it can also control energy absorption from the AC system to keep the storage device charged. So this potential capability provides a new tool for enhancing dynamic compensation, improving power system efficiency and potentiality, preventing power outages. So by using this potential capability, we have new tool for enhancing dynamic compensation, improving power system efficiency and potentiality, and preventing power outages. And next, the reactive and real power exchange between the STATCOM and the AC system can be controlled independently of each other, and any combination of real power generation and absorption with VAR generation and absorption is achievable. So here I am taking both power exchanges, that is real and reactive power exchange between the STATCOM and AC system. So these can be controlled independently to each other, and any combination of real power generation and absorption with VAR generation and absorption is achievable. So thus, by equipping the STATCOM with an energy storage device of suitable capacity, so it is extremely effective control strategies for the modulation of reactive and real power exchange can be executed for the improvement of transient stability and the damping of power oscillations. So it should be noted that for short-term dynamic disturbances, an energy consuming device, that is switched resistor, may be effectively used in place of the more expensive energy storage to absorb power from the AC system via the STATCOM. Okay. Next, so with this simple scheme, the STATCOM would transfer energy from the AC system to the DC terminals, where it would be dissipated by energy consuming device. So that means either battery or superconducting material like that. So that would be switched on whenever surplus energy at those terminals is detected, that is by increasing the DC voltage. So with this simple scheme, the STATCOM would transfer energy from the AC system to the DC terminals. So at that time it will dissipate the energy consuming. It is dissipated by the energy consuming. So and the next comparative characteristic is operation with unbalanced AC system. Operation with unbalanced AC system. So actually the AC system voltages are normally balanced. You know already this point. The AC system voltages are normally balanced, but maximum unbalance does not usually exceed 1%. Okay, and therefore compensators normally control all three phases of their output current together. So thus for the SVC normally means that its control establishes three identical shunt admittances, one for each phase. So consequently, with unbalanced system voltages, the compensating currents in each phase would become different. So it is possible to control the three compensating admittances individually by adjusting the delay angle of the TCR, that is thyristor controlled reactors, so as to make the three compensating currents identical. So here we are using three compensating admittances. So to control the three compensating admittances, we have to adjust the delay angle of the TCR. Why? Because to make the three compensating currents identical. So however, in this case, the triple N harmonic content would be different in each phase. So, and their nominal cancellation through delta connection would not take place. So this operation mode thus would generally require the installation of the usually unneeded third harmonic filters. Okay. So the operation mode thus would generally require the installation of the usually unneeded third harmonic filters. So for this reason, individual phase control for SVC in transmission line compensation is rarely employed. So that means SVC is rarely employed for the transmission line compensation. So the operation of the STATCOM under unbalanced system conditions is different from that of the SVC, but the consequences of such operation are similar. Only operation is different, but the consequences of such operation are similar for the both SVC and STATCOM. So the STATCOM operation is governed by the fundamental physical law. Okay, the STATCOM operation is governed by the fundamental physical law requiring that the net instantaneous power at the AC and DC terminals of the VSC, that is voltage source converter, employed must always be equal. So this is because the converter has no internal energy storage. So for the STATCOM we don't use any internal energy storage, and thus energy transfer through it is absolutely direct, and consequently the net instantaneous power at its AC and DC terminals must be equal. So assume that the DC terminal voltage of the STATCOM is supported entirely by an appropriately changed DC capacitor, and that the losses of the converter are zero and its pulse number is infinite. So here I am assuming these things, and with perfectly balanced sinusoidal AC terminal voltages, the STATCOM will draw a set of balanced sinusoidal currents in quadrature with the system voltages. Okay, but the DC capacitor will experience no charging current. Okay, the DC capacitor will experience no charging current because no real power is exchanged with the AC system. And furthermore, because the net instantaneous power remains invariably zero at the AC terminals of the converter. So, however, if the AC system voltages becomes unbalanced, then an alternating power component at twice the fundamental frequency will appear at the AC terminals of the STATCOM converter, and this will be matched by an alternating second harmonic charging current in the DC terminals and producing in turn an associated alternating voltage component of the same frequency across the capacitor shunting the DC terminals. So like this we are taking the operation exchangeable powers. So if the converter control ignores this AC voltage component, so that is if it is operated to produce the AC output voltage as if the DC terminals voltage was constant, then the secondary harmonic voltage component from the DC terminal will be transferred as a negative sequence fundamental component and a positive sequence third harmonic component to the AC terminals. As a result, the STATCOM will in general draw a negative sequence fundamental current component, as well as a third harmonic current component. Likewise, that is producing. So, out of the two voltage components generated in the output of the STATCOM, As a result of the system unbalance, the third harmonic is clearly unwanted. The third harmonic is clearly unwanted. Whereas the negative sequence of fundamental voltage generated naturally by the converter with properly sized DC capacitors reduces significantly. So the negative sequence current that would otherwise be forced to follow by the negative sequence system voltage. So that means the third harmonic has clearly no useful function. So the natural behavior of the STATCOM is illustrated in the figure, that is this one. So this gives the waveforms illustrating the operation of a STATCOM without individual phase voltage control during and following a line to ground faults at the regulated bus. Okay, so that means the natural behavior of the STATCOM is illustrated in the figure, where relevant voltage and current waveforms records representing a TNA simulated power system with a precisely scaled 48 pulse STATCOM hardware model that was subjected to a severe line to ground fault. That is this one. So here we have voltage and current waveforms and a reference signal waveforms like this. This is at the without individual phase voltage control during the faults, line to ground faults. So here VAB and VCB waveforms are sinusoidal waveforms, and next we have IA, IB and IC. Those are changes. So if you observe this one, there is a change in the sinusoidal waveform. So this is because fault in the phase. Okay, next coming to the VDC, that is the output voltage. We have the waveform like this, and coming to the reference signal, reference current, reactive current. So the waveform is like this. So the traces in the figure shown, that is from top to bottom, line to line voltages VAB and VCB, that is phase A is faulted to ground. Phase A is faulted to ground. So the three currents drawn by the STATCOM, that is IA, IB, IC, and the DC capacitor voltage, that is VDC, and the reactive current reference, that is IQ reference, limited to 2 per unit. So in steady state, the STATCOM was producing 1 per unit capacitive current when it was subjected to a line to ground fault lasting for about 5 cycles. That's why I am taking 5 cycles. Okay. Next, so it can be observed that in steady state, the STATCOM was producing 1 per unit capacitive current when it was subjected to a line to ground fault lasting for about 5 cycles. So it can be observed that due to the internally generated negative sequence converter voltage, okay, due to internally generated negative sequence current voltage, converter voltage, the STATCOM was providing during the fault substantially balanced and capacitor compensating currents with maximum magnitude of 2 per unit, but with considerable third harmonic distortion. So, however, the harmonics present only during the 5 cycle fault period are arguably of no significant consequence. No significant consequence. So, on the other hand, STATCOM, as evidenced in the figure by the capacitive compensation maintained, can provide strong system support during the fault. So, this with the STATCOM's faster response at fault clearing could greatly contribute to system stability. So, the natural behavior of the STATCOM characterized the conditions related to the operating mode in which the three output voltages, that is VA, VB, VC, are controlled together, that is single phase voltage control is not applied. So this operating mode provides the best VA utilization of the converter and generally the lowest harmonic generation obtainable under normal system conditions with a given method of waveform synthesis employed. So that is TNA method. So however, in special applications where considerable system unbalance exists, okay, or where large unbalanced loads are to be compensated, the STATCOM converter with appropriate pole structure and waveform synthesis method can be operated to control each of the output phases individually. So that is to control the positive and negative sequence compensating currents independently. So however, this type of operation is usually associated with some amount of fluctuating AC power and therefore it requires a larger DC capacitor than typically used in a transmission system STATCOM to accommodate the consequent second harmonic ripple current at the DC terminals. Okay, thank you. So in the next class, I'm going to discuss remaining comparisons. Hardly we have two more comparisons between SVC and STATCOM. I will continue this class in the next section. Okay, thank you. Thank you for watching this video.